by thanking him for inviting me and putting together this nice workshop. So I'm going to tell you about some very recent work of ours on doing Monte Carlo evaluations for wave functions that are constructed from CFDs. So this is work done in collaboration with Koena Bose, who's my graduate student, and Steve Simon, who's at Oxford. I'd like to thank generous funding from the Science and Engineering Research Board. I have a matrix grant from them. And we'd like to make a special mention to this coding package called DIGHAM, which we use extensively for many of our numerical computations. Okay, so the preprint is not yet out, but I put some pressure on myself to get it out. This will hopefully come out by the end of this month. 25, yeah. Okay, so the plan of the talk is as follows. I'll tell you very quickly about integer quantum Hall effect. This is basically to set the stage. Most of you know this stuff very well. Then I'll go to the main part of the talk, which is about fractional Hall effect. Then our new progress on this, on how to compute using Monte Carlo wave functions, quantities for wave functions that are constructed from CFD. So you will see that if you just use a naive way to look at these wave functions, they're extremely hard to evaluate. But there's some nice tricks to get around that and then make computations of fairly large system sizes. And then I'll end with some conclusions and out. Okay, so I think amongst the speakers at this workshop, I'm probably the one who's closely connected to experimental, very close connection to experiments. So let me start off by telling you about one of the experiments that kind of like started off this field. So this is this Klaus von Klitzing's discovery of the integer Hall effect. So what Klitzing did in 1980 was took a two-dimensional system of electrons, placed it in a strong perpendicular magnetic field, ran the current one way and measured the voltage in the transverse direction. And what he found, very surprisingly, that this ratio of the transverse voltage to the longitudinal current is exquisitely quantized in units of h over e square. So this number n here turns out to be an integer. And this is kind of like very independent of things like what kind of sample you use, what kind of disorder the sample has, what kind of geometry you put the system in, and so on. And this quantization is now like accurate to about a part in a billion. So just I think like from 2 years ago, the Klitzing constant, which is this h over e square, and this Josephson effect, which measures the flux quantum h over e, these two effects put together pin at h and e for us. So these are the measurements that fix these fundamental constants. So you can see these plateaus at integer values of h over e square. And concomitantly, what he also saw was that if you look at the longitudinal resistance, that is actually suppressed. So that means there is like prohibition of transport through the bulk. So this is like a gapped state that forms, and that has macroscopic quantization. You measure resistance, which is over many micrometers, and that actually happens to be quantized. So integer Hall effect is somewhat like easy to understand. IQHE just arises from the formation of Landau levels. So if you take a non-interacting Fermi gas and put it in a perpendicular magnetic field, the spectrum of it splits into many degenerate bands, which we call Landau levels. And whenever you have an integer number of these filled, you get integer Hall effect. It's a fairly simple picture. And it's also easy to understand things like where does the gap come from. So the gap just comes from the fact that there is a cyclotron gap to the next Landau level, which is just proportional to the field. So if you crack up the field, you can make the cyclotron gap very large. And then the additional ingredient you need is disorder. So you get a plateau in Hall resistance because there are some localized states that are formed because of disorder. And even though you add electrons or you like change the field, the disorder traps these electrons into local orbitals and they don't move and they don't contribute to transports. That's why you get a plateau in the resistance. So these two ingredients, just pure non-interacting physics, Anderson localization and formation of Landau levels, is sufficient to explain integer Hall. Okay, so the focus of this talk will be on wave functions. So how do we write down some microscopic wave function to describe these states? Okay, and the simplest wave function that you will see in this talk is the wave function of one fill Landau level. So that wave function has this typical form, which is product I less than j, zi minus zj, and a Gaussian factor. So how do I get a wave function like this? So if you remember quantum mechanics of a single particle in a magnetic field, then these Landau levels, in particular the lowest Landau level, has orbitals of the form z to the n, where z is this two-dimensional coordinate parameterized as a complex number. So z is just x minus iy. So now what I do is that if I want to fill one Landau level, I fill all the orbitals in the lowest Landau level. So I make a slated determinant state of electrons where I fill all the orbitals from 1, z to the 1, z to the 2, and so on. And that gives me exactly this wave function. Okay, so Maybe as a homework, you should just go look at this determinant and see you get this. But let me tell you why one can just immediately say that this has to be the wave function. Because electrons are fermions. So every electron has to see a zero at every other electron. And that alone fixes this form of the wave function. So this always has to be a factor of any wave function that resides in the lowest Landau. Because wave functions are polynomials in Z's. And every electron has to see a zero at every other electron. And this is exactly doing that. You put all the zeros at every other electron. And this Gaussian factor, which I'm going to ignore throughout this talk, just comes from Landau level physics. So that has got that won't be relevant in this talk at all. So we will mostly look at this part, which we usually call some correlation information. And that is what we'll concern ourselves with. So one curious fact is that wave function of other fill Landau levels are not known. So we don't know how to write down a wave function for two fill Landau levels in some closed form. So one fill Landau level has this very nice form. This is also called the Vandermonde determinant. But filling two Landau levels, three Landau levels, you can construct them by a slated determinant, but they don't reduce to any simple form. Okay. But then you should just feel free to stop me and ask questions. I mean, I have about 30 slides, so I won't get to 1.5 hours unless you stop. Okay. So very soon after Klitzing's discovery, Sui, Stommer, and Gossard made much better samples, went to much higher fields, and kind of repeated this experiment. And what they found very curiously and very surprisingly at that time was that the Hall resistance has a plateau at h over 1/3 e square. And concomitantly, again, the longitudinal resistance shows a gap.
So when you say much better samples, you mean much smaller disorder?
Yes, the mobility is higher. That's another way to say it. Lower disorder. Yeah. So actually, it seems like Sui remarked that he had seen quarks in a condensed matter system, and then somebody politely told him that there is a difference between capital MeV and small MeV. This is a much lower scale, and quarks are not at all relevant here. So somehow, like electrons get together to form a state which gives you a quantized resistance at. There's some fractionalization in this quantized resistance.
So in the earlier graph, we mentioned that it does not depend on the geometry and the disorder.
Same thing holds here.
So how do you distinguish between these?
The value of the Hall resistance is different. So this is a resistance which is h over 1/3 e square. That has a resistance which is h over e square. So you always get some number which is like h over n e square, where n, if it's integer, is integer Hall effect. If it's fractional, is fractional Hall effect. That's all. Okay, so FKG, it turns out, is an extremely hard problem. So one nice limit to think about the FKG problem is this limit where you send the cyclotron frequency to infinity. So all of my physics is completely confined to the lowest Landau level. And there the problem admits a very simple interpretation. So once you are in the lowest Landau level, the kinetic energy is completely quenched, right? Because all the electrons have half h bar omega c kinetic energy, which is just a constant of the problem which you can throw out. So now the only thing that is there in this problem is interactions between electrons. So electrons are charged particles. They always interact via Coulomb forces. So the Hamiltonian is kind of like very simple to describe. The Hamiltonian is just this: E square over epsilon, some I less than j, 1 over mod zi minus ej. So one curious fact is, if you look at a Hamiltonian like this, it looks very classical, right? There's no like quantum mechanics. It seems like there's no quantum mechanics in this problem. But that's not true. So what happens is, once you project the coordinates to the lowest Landau level, they don't commute anymore. So if you look at the lowest Landau level projected x and y, they have a commutation relation which is I times L square, where L is a characteristic length in this problem, which is the magnetic length. And somehow what the experiment is telling us is that interactions in some way go on to pick one unique state. So I say one unique state because we know there is a gap to this system. So interactions are picking out some unique state from a highly degenerate manifold. So let's say if I had no interactions and I give you some fraction like 1/3 or 2/5, then in terms of describing that problem in terms of like some basis states, you have like 4 electrons in 10 orbitals. So that's filling 2/5. So this filling factor is just the number of particles divided by the number of states you have available. So there are like roughly 10 choose 4 ways of dividing, of putting 4 particles in 10 orbitals. But then of all of these ways, somehow one particular state emerges which minimizes the Coulomb energy. And that is what is seen in the experiment. And that's what the experiment is kind of telling you. But now if you like, let's say crank up n, then the number of such basis states is really high, right? It's like n over nu choose n. That's a humongous number as n goes very large. So how am I going to like come up with a state which is a linear superposition of so many of these, which somehow like magically captures the exact unique state that is seen in the experiment? So another usual technique of ours, which kind of completely fails here, is perturbation theory, because there is no small parameter in this problem to expand around. So the only thing you have in this problem is this Hamiltonian. there is no like normal state around which you can perturb. So if you just go back to switching off this interaction, you just get a degenerate mess. There is no, you should contrast this with things like superconductivity, where if you like switch off the attractive interaction between electrons, then the state you get is a Fermi liquid, which is a unique state, which is easy to understand and so on. But here, that's not the case. The moment you switch off the interaction, you just get a big degenerate mess. So how do we make any progress at all in this? So the path forward was shown by Laughlin, who just made a guess for what the state should be at filling factor 1 over m. So what Laughlin proposed was that the wave function at filling factor 1 over m, ground state wave function should be of this form, which is like zi minus zj to the power n. And because these are fermions, this m has to be an odd integer. So what was Laughlin's logic for this? So we want to minimize Coulomb repulsion. So what I want to do is when I bring two electrons close together, I want to make sure that they vanish, the wave function of these electrons vanish faster than just what is mandated by Pauli principle. That's exactly what this does. So if you look at the
Sorry,
mod,
isn't it
yes,
very nice? But
Yeah.
So it's all if we can we see this in which we put the magnetic field in this area?
if you have a 2-deck which has sufficiently low disorder, you will be able to see it.
And what's the reason that I mean we are only considering say Coulomb interaction?
You don't have to. We don't have to necessarily restrict ourselves to
So
Coulomb.
even if there is some electron form like those are.
I mean, let's forget about phonons. Let's not bring phonons. Let's say you have some other interaction even between electrons. Let's say some dipolar coupling, or let's say you are not having exact Coulomb, but you have some Coulomb that's screened by some gates in this material. Still, you will see this. So it's fairly universal.
Long as it's a repulsive.
No, even attractive interactions can, in principle.
For attractive interactions.
No, it doesn't have to be electrons. It doesn't have to be like, so let's say you have some bosons and they have some attractive interaction. They can form some special kinds of FTs. It's possible.
Because they are hardcore.
Yeah, they're hardcore. Yeah.
So secretly there is a repulsion.
Yeah.
But it depends on the power of the power law follow or.
No, it doesn't even have to be like a power law interaction. Let's say you have a Yukawa type interaction that will show this feature. So non-universal features like what is like the gap of the state, that depends on the form of the interaction. But the basic physics of this having like a gap state with some incompressibility gap, that appears very generically. That's not very sensitive to the precise form of the interaction.
So all this tells you that it's a topological state.
Yeah, I didn't want to utter that word, but okay. Yeah, that's kind of, this topological feature also explains why it's so universal. Like you don't you don't have any sensitive dependence to like disorder, sample geometry and things like that. Okay, so what I was saying was that if you look at like mod psi 1 over m Laughlin square, let's say I fix one particle to be at the origin. Let's say z1 I set to 0 and I put z2 at another particle coordinate, which is at some distance r. Then if you look at what is the vanishing rate of this wave function, then mod psi square vanishes as r to the 6th. So that vanishes extremely fast. So if you now look at the Coulomb expectation value, which is like integral mod psi square 1 over r, then that dies very quickly. So it's like a good ansatz to minimize Coulomb repulsion. That was the basic idea. So as I said, for fermions, this m has to be odd integer, and for bosons, this m will be some even integer. So one question you can ask is how do I look at this wave function and say that it's at some filling factor which is like 1 over m? So if you look at Landau orbits, then these Landau orbits have functional form z to the power n. Okay, so I have, let's say, like n particles, and I ask what is the largest orbit that's occupied. So what is the maximum power of z1, let's say. So if you look at the maximum power of z1 here, that's roughly like m times n minus 1. Right? Because I have zeros at every other electron. So I get n minus 1 powers of z1 in this polynomial. If I just expand this polynomial, that's what I'll get. And m powers of that. So the filling factor is the number of particles divided by this largest power. So it's n over m times n minus 1, which in the large n limit goes to 1 over m. So that's why the state sits at filling factor 1 over m. So Laughlin showed that this wave function actually has some amazing properties. So if you look at excitation, so this is the ground state wave function, but now you can look at what are the excitations of this state. He showed that these excitations actually carry fractional charge. So if you look at the minimally charged quasi-particle or quasi-hole of this state, that has a charge which is E over n. So this is like some beauty of emergence that happens, that in a system where you had only electrons to begin with, suddenly particles which have like quantum numbers that are fraction of electron show up. That happens. Moreover, Aruba, Schiefer, and Wilczek, very soon after Laughlin's work, showed that if you look at like the braiding statistics of these quasi-holes, so let's say I take a quasi-hole, I go around another, and look at what is the phase that's picked up, that's actually a fraction of that of bosons or fermions. So if you have two bosons, you go around another, you pick up a phase which is 0. Fermions pick up a phase which is pi -1. Whereas these Laughlin quasi-holes and quasi-particles, they pick up a phase which is like 2 pi by n. Okay, so this is a very exotic state that somehow is like, that's showing up in experiments.
What experiment you did this space?
So there are these fractional statistics experiments that were done very recently. So there are two experiments, one in which you let's say have, you make an edge and then you tunnel quasi-holes in two different paths and interfere them. And you ask, how does the resistance change as a function of this path length? Then this phase shows up. The other experiment is this so-called anion collider, where let's say if you let's say I shoot two fermions close together, they will repel each other. If I shoot two bosons close together, they will attract. And anything in between is like anionic. So that was what was done recently. Okay, so we now want to check how good is Laughlin's description for the actual ground state. Okay, so it seems like a reasonable.
It's a good question probably. So in the previous slide, in the wave function, what told us about the fact that we have fractional charges?
No, nothing has, that I have not told you. That was established later by Laughlin using what is called a plasma analogy. So that part I'm not covering. So you can interpret this wave function as the wave function of a 2D Coulomb gas or two-dimensional one-component plasma. And then if you look at the quasi-hole wave function, you can show that that quasi-hole is like adding an E over M particle on top of the background. So that part I haven't established. But that Laughlin showed by mapping the problem to that. You have to take my word for it.
So this wave function, it's an answer and then was verified or?
I'm going to show the verification. Yeah. Okay, so yeah, to show how good this wave function is, I'm going to pick some geometry, some 2-deck geometry. So lots of choices of 2-deck geometries you can pick. So the simplest thing that comes to mind is you pick something like disk, because I mean that's the natural planar 2D geometry. But disk actually has some problems in that if you don't keep any confinement, then repulsive particles will just fly out infinity.
The ninth question regarding
Yeah.
these E by M over.
Yeah.
If you go back, that's of course the ground state ansatz or something.
Yeah.
Right. So of course I know how to add an electron or subtract an electron in a simple way in an operator sense.
Yeah.
And there's a non-trivial projection here. So somehow, okay, then if I add or subtract an electron and do this non-trivial projection, somehow this fractionalization should come out.
It will. If you just wait for some more time, I'm going to show that.
Yeah.
What is the wave function for a quasi-hole will come
Yeah.
few slides down the line, and then you can kind of see that it has charge over it.
No, what I was wondering is if I take this simple operator for
Yeah.
E or
But that is like adding 3 of these. No, that's a
Yeah.
very high energy excitation. I don't want to do something like that. So the lowest energy excitations in this system are going to be E over M particles. So I want to show how to add that. I mean, I can tell you what adding the electron looks like. So you multiply this thing by product I, Zi to the power 3. That is like adding 3 quasi-holes. If you now remove this factor of 3 and add just 1, that is like adding E over M particle. So one way to think about this is that every electron now occupies for itself 3 orbitals. Okay, so when I now multiply by product over I, Zi, I shift all the orbitals out. Okay, but when I do this, I shifted only 1 orbital out. So that's like shifting 1/3 of a charge out. So now if I do 3 of these together, then I will shift a full hole out. So that's one way to see the fractional charge. Okay. So I'm going to pick this. So I was saying that the problem with the disk is that if you don't put any confinement, then the particles will all go away to infinity. So we don't want to use that geometry. So then things are like sensitive to what kind of confinement you put and so on. So it's best to use some compact geometry, because throughout this talk, we're going to mostly be concerned with only bulk physics. So I don't want to bring the edge at all into the picture. So for bulk physics, there are 2 good geometries. One is to use a torus or to use a sphere. So torus has this issue that it has a genus which is like non-trivial. So usually ground states then appear with some degeneracy. So again, I don't want to get into any of that. So I'm going to just pick the sphere, which is nice compact geometry where ground states are non-degenerate. But then this is the same sphere that is becoming recently very popular in the conformal field theory domain. This comes by the name fuzzy sphere geometry. This is what Haldane constructed. So what you do is that in this geometry, you pick a magnetic monopole. Okay, so for a theorist like me, that's no problem, but you just get hold of a magnetic monopole, place it at the center of the sphere, and that generates this radial field, which is like analogous to the perpendicular magnetic field that you had in the plane. And you just wrap the plane on the surface of this field. Okay, and appropriate to this geometry, the orbital angular momentum and its z component are usual good quantum number. So that's all. Now what you do is that you just place some number of electrons in this geometry, solve the Coulomb problem, and check how good Laughlin represents the actual eigenstate.
So why does it call it fuzzy sphere? What is fuzzy about?
Yeah, so okay, that's kind of taking us too far. So the fuzzy part is that if you, let's say, look at like Landau levels, then these Landau levels are not like point-like objects. They are slightly diffused in nature. And that is what is called this fuzzification.
Because the whole packet has a width.
Wave packet has some width. Yeah. So for example, if you wanted, let's say, the issue in conformal field theories for a long time has been like, if you like simulate some lattice system on, then you always end up with some defects. So this kind of gets rid of that because you always like make some, it's not like a point-like defect. It has some extent.
So on the computer, what do? You just take a lattice on a sphere and you put a magnetic field.
I'm not taking any lattice. I'm going to solve the continuum problem.
I see.
That's the whole point. I don't want to get into a lattice.
Wait, is this non-commutative in some sense?
Yes. So just as I said, what I'm going to do eventually is to project to the lowest Landau level. Then the coordinates in the two directions will not commute. Yeah, x and y don't commute anymore once you project to the lowest Landau.
But before you do that,
Then everything commutes. But then the problem is the Hilbert space is too much for us to solve because then all Landau levels have to be kept. So that makes the problem impractical. Okay, so we need one way to parameterize the interaction. So that again, Duncan showed how to parameterize the interaction. It's this idea of what are called Haldane pseudopotentials. So the way you construct these Coulomb matrix elements is by this idea of Haldane pseudopotentials, which just tells you what is the energy cost of placing two electrons in some relative angular momentum state. So remember, in this geometry, angular momentum is a good quantum number. So now I can place electrons in some angular momentum state and ask what is the energy penalty that Coulomb gives to them. And for just standard 1/r Coulomb, you get this typical decay. So this is the angular momentum at which the electrons are closest together. So that has the highest penalty. And then it decays in this typical 1/r form. So for example, if you change the interaction, these pseudopotentials will change. But as long as these pseudopotentials are dominated by this small m part, you will see that Laughlin is very good. And the reason for that is that the Laughlin state is the exact ground state where you remove the m equal to 1 pseudopotential. See, the Laughlin, for any fermions can have any relative angular momentum that's an odd integer. And what Laughlin state does is that it removes relative angular momentum 1. It has a zi minus zj to the power 3 and so on. So that means no two electrons can come close together in relative angular momentum. And the idea is that Coulomb and any of these interactions that are sufficiently strongly repulsive at short distances, they penalize this relative angular momentum 1 state. So Laughlin does an excellent job of removing that. That's basically the idea. Okay. Okay, so then you just take this problem, just brute force diagonalize, and then check what is the overlap of the Laughlin state with the exact ground state. So you can do this for about like 15 particles at 1/3, about 11 particles at 1/5. So the Hilbert space dimension is like 2 billion. Okay? And if you look at what is the overlap of the exact Coulomb ground state with the Laughlin state, that's like 99%. So the real thing to appreciate here is that if you had taken a random vector of size 2 billion and asked what would its overlap be with the exact Coulomb ground state, it would be essentially 0. So Laughlin not just captures the right universality topology of the state, it actually captures it almost microscopically exact. Okay. That's like an amazing thing. So usually that never happens. If you write an ansatz for a strongly correlated state, you kind of expect that it will be in the right universality class or it will be in the right phase. But here you get an almost exact microscopic description of what the state is. Okay. So one thing you can ask is why do this only for 15 particles and so on? Why not do it for larger sizes? So the problem is that anytime you do a computation like this, the Hilbert space just grows very quickly. So as you saw for 15 particles, if you look at the Coulomb matrix, that has a dimension which is like 10 billion cross 10 billion. I mean, not all of these matrix elements are actually occupied. So it's a fairly sparse matrix. But for a size of a billion dimensional matrix, you can basically just get the ground state for a sparse matrix. So if I now, let's say, get to 20 billion and so on, that problem is not diagonalizable anymore. Simply because the Fock space grows very quickly, right? So this state actually roughly has a size which is like 45 choose 15. But then I use all of these symmetries on the sphere. I make sure that things are in the angular momentum 0 state because I'm looking for a uniform state and so on. So that kind of brings down the size to roughly like 2 billion, which you then have to diagonalize. So it'd be much nicer if we can find some other technique to like simulate the Laughlin wave function for much larger sizes.
So, I mean, here.
Yeah.
The last slide, so how far do you take for these elements?
So here you take the whole thing because you see for any finite system, there is only a finite number of pseudo potentials. So then that is just put by the truncation you have. So let's say if you have 15 particles, then the maximum angular momentum could be like 45 or something like that, roughly 3 times that.
Okay, it's all,
So you can take all of them. Yeah, and the main point is if you just truncate at m equal to 1, then you get Laughlin state exactly. So I can also construct Laughlin state in Fock space like this.
if you take only n equal to 1.
Yeah, I let's say set all of these to 0, and I say there's like a delta function here, then the exact ground state is Laughlin. Otherwise, the exact ground state is like 99% close to Laughlin.
In that case, I will go.
Both these numbers improve if you increase n.
No, they will always decrease. So the reason is that unless you have an exact state, states in the thermodynamic limit will always be orthogonal to each other. This is what is called as Anderson's orthogonal catastrophe. So you can think of it as like in every basis state you have some finite difference. And as n grows, that number will grow. So eventually 2 states that are not exactly the same will always be orthogonal in the thermodynamic limit. But the question you ask is how slowly does the overlap go to 0? Okay, so here it will go exponentially slowly with an exponent that's really tiny. Any 2 states that are not exact will always be orthogonal in the thermodynamic.
So this is the best possible match for some value of mu and some value of n.
So this is the best you can do for 1/3. Yeah, I haven't made any comments.
I compute some observable.
Yeah, that's what I was going to say. So you don't have to take overlap alone. So you can do other checks, like you can compute some topological number and check whether that matches for the exact state and the Laughlin state, and that does. So one thing you can do is what is called an entanglement spectrum. So you make an artificial cut on the sphere. So let's say I divide the sphere into a northern hemisphere and a southern hemisphere. Then this artificial cut serves like an edge of the system. And we believe that for topological state, there is this bulk boundary correspondence that holds. So anytime you get some edge in the system and you get some signatures of the edge, that also carries the topological fingerprint of the bulk. So now if you compute the entanglement spectrum of the 1/3 Coulomb ground state and 1/3 Laughlin, their edge countings will be identical. That you can show. Yeah. I mean, overlap is after all just a number, no? So that number will always go to 0 in the thermodynamic, unless you have 2 exact same states. Okay. Yeah, all other observables that you can calculate, like filling factor, any topological number you can calculate for these 2 will be identical.
So there is no activity on improving the.
It's already pretty good, sir. We don't care so much about it.
Just.
Not really, not for Laughlin. No. I mean, there are ways that people know of improving, but usually this is the thing that, so this is usually a terrible way to construct Ansatz wave function, because when you, let's say, make a trial state, you usually put some variational parameters in it and then try to optimize. I'm not doing any of that here. So I just gave you a wave function. So it's either going to be hit or it's going to be missed. So but what happens in topological systems is that if it hits, then it doesn't matter and nothing else matters, because as long as it captures the right topological properties, you're okay. You don't care so much about microscopic details. Here, it's just like a coincidence that the microscopic details also come out really well.
So just to be, are the negative do some sort of transport? Is that also some topological?
Yeah, here the transport was topological because you saw the Hall resistance has a quantized number. So that will come out to be the same. But for example, the longitudinal resistance depends on what is the gap. That is a non-universal number. That will not come out to be the same. But a response that is topological will come out.
The fact that it's E over 3,
Yeah.
1/3 is topological.
That is topological, yeah. Or h over 1/3 e square, that 1/3 is topological. It's a number that you cannot continuously change. Okay. Okay, so with Laughlin, you can actually do some more. You can do Monte Carlo. That's the big advantage of having Laughlin's wave function because you have a very simple form that's given to you in real space. So it's just product I less than j, zi minus ej, that's all. So this is roughly has complexity, which is like n minus 1, right? Let's say if the power of m is like 1, then this just has you have to do just n minus 1, there are only n minus 1 terms per z1. So we can, for example, compute what is the pair correlation function for Laughlin state for 500 particles. So if you look at the Hilbert space of this, that's upwards of 10 to the power 400. So, okay, that's just not going to be possible with any exact diagonalization. But with Monte Carlo, you can get things like this very nice. And this kind of shows lots of properties of the Laughlin state. So firstly, it tells you that this small distance behavior of the Laughlin state is indeed like r to the 6th. So if you, let's say, look at how g of r goes as a function of r and the small r limit, you can show that this will go as r to the 6th. Then it also tells you that this is like a liquid state. It doesn't have any like special peaks. Like if you had a charge density wave, you would get some special peaks if you computed the structure factor. So if you compute the structure factor of this, this will look exactly like that of a liquid. So very far away from, so what does the pair correlation function say? It just says that if I have a particle at the origin, what is the probability of finding another particle at some distance r away? So if I go very far away from the origin, then all of these like short range correlations go away and then it just goes back to the uniform density. So you have a uniform density liquid and this number goes exactly to that density. That's what is shown with this. So yeah, so this is the main point of the talk. So if you can find some nice wave function which has a form that is expressible in real space, then you can do Monte Carlo with it for gigantic systems, which may not always be possible if the form of the wave function is not readily amenable to numerics. So actually for Laughlin, as I said, there is also this plasma analogy that was extensively used to get many of its properties.
So this is not on a sphere in.
This is on a sphere.
It's on a sphere, but how do you define the R?
You can define as arc length, that's what it is. Yeah. Or you can define at chord length, it doesn't matter so much. So once you go to a large enough R, chord length, arc length differences will go away.
So to get this kind of is more power, how many Monte Carlo states one?
Yeah, so this requires about like 10 to the 6, a million. But you can do this very quickly because the wave function is just so easy to evaluate. Okay. Okay, so now I'm going to tell you some CFT connection to this. Yeah.
Question. So, you said that you can do this Monte Carlo thing and probably calculate local correlation system.
Yeah, yeah.
But suppose you want to calculate these entanglement and stuff.
That is
you
hard.
also do that using Monte Carlo?
You can, yeah. So there is one version of entanglement which you can do, which is called the real space entanglement spectrum. That one can do with Monte Carlo. So there is a trick to doing that. That was developed by Steve Simon and company. So that you can do, but orbital entanglement spectrum you cannot. Because when you need to do orbital entanglement spectrum, you need the decomposition of the Laughlin state in the orbital basis. That is very difficult to get. But in Landau levels, you kind of get lucky because the orbital picture is the same as the real space picture because of this fact that the coordinate y is like k times L square. So the real space coordinate is connected to the momentum coordinate. So then the real space entanglement and the orbital space entanglement give you the same signatures. And real space we can do for much larger.
So what does this oscillation do? So like there are some small oscillations.
Yeah.
In same scales.
Yeah. So what happens is that because when you created the Laughlin state, you like removed particle. Let's say I fix one particle. Let's say I look at Z1. Okay. Then near that I created a correlation hole. So now that density has to go somewhere else and it will create a bump compared to the background density. That's all this is. So all the particles which are excluded from here, they kind of went away and sat there. Sorry.
I'll ask you the same question. What does this mean?
Yeah, that's all. It just says that at some distance, the correlation is really tight and it excludes particles here. So then at some point, the density has to be more than the background density. Because overall, I have uniform density. If I just integrate all the particles over this, I should get the total number of particles. So if I suppress the density somewhere, I have to get some density higher somewhere else. That is what. At some point, the density is above the background density.
Also from the pair correlation, can we read off what is the average spacing between the particles?
I mean, average spacing you can just read off from the density. So you don't need pair correlation for that.
Yeah.
Okay, good. Okay, so now what is the CFT connection to the Laughlin state? Okay, so it turns out that the Laughlin's wave function can actually be written as a CFT correlator. So this was found out by Moore and Reed in a seminal work that came out in the early 90s. And their approach to this was via the edge theory. So
Is this in particular the 1/3 space, or are you?
no, this is for any 1 over m.
Any 1/m?
M,
Okay.
yeah. So you can look at the Laughlin state as this. Yeah, this is just a function of n. That's all. The thing that I'm going to tell you about correlators and so on will even work for m being even. Even when the wave function is describing bosons, the CFT correlator idea will still work.
The hard part is on the numerator is not one.
That's the problem, yeah. Okay. I mean, when the numerator is one, it's like a non-interactive problem. Everything can be worked out exactly for that. So let's say if you want the pair correlation function, it's just 1 minus e to the power minus r square by l square. That's all. Because that's a non-interacting state. No, I can just work out everything for it. For nu equal to 1, it's just a slated determinant. Only for nu that's not equal to 1, where, as he said, the numerator is greater than, nothing can be worked out exactly. That's an interacting state. This is point clear or?
When you're asking me?
Yeah.
Yeah.
Yeah, of course. Yeah, we kind of are interested only in m greater than 1. Let's put it that way. Okay. So what they noticed was that if you consider a free chiral Bose field, which takes this form, so phi of z is just e to the I 2 pi m x plus I tau. So z is just x plus I tau, and b is a Bose operator. Then this 2-point correlator has this particular form, which is like minus log z minus e. Okay, so one home assignment is to like try and show that this is true. If you take this as the host, I don't know if Connor did this yesterday, maybe, or maybe this is like, yeah. So it's somewhat tedious to show this, but it's true. So what they did was they defined these so-called vertex operators, so which is like this v alpha to the z, which is normal ordered e to the I alpha phi z. Okay, and using Wick's theorem, you can actually show that if you look at the average of v, by which I mean v alpha 1 z1, v alpha 2 z2, and so on. If you look at this average matrix element, then this has this very special form, which is like e to the minus I sum over I less than j, alpha j, phi z I, phi z j. Okay, and then you use this fact that phi z prime is this. With that, you can show that this average v is like product I less than j, zi minus zj to the power alpha I. So there is some subtlety involved in this. So you also need this condition that the sum over alpha I has to be 0. And the reason for that is that this phi has a U1 symmetry, which is you can move phi by some a. So if you move phi by some a, then this b to the power alpha moves as e to the I alpha times a. And this has to be a pure phase. That phase has to be 1 exactly. And that is just fixed by this condition. Okay. So that's why you need this condition. So this is sometimes in the quantum Hall literature, this will go as background neutrality condition. I don't know what it's called in the CFT literature. Okay, so this is the main result, that this matrix element has this form. And now you can kind of like see what you need to do to get Laughlin from this.
How is the normal ordering defined?
So the normal ordering is defined in the standard way. You bring all the b's to the all the creation operators to the left of the annihilation operators. Okay. So now what you can do is you define an electron operator, which is just the vertex operator, and you choose this alpha to be square root of.
Like the background neutrality condition can be related to the like from plasma analogy.
Yes, so you have to tweak the background to get the Gaussian factor. Basically, that is what you need to do.
Right.
Yeah, kind of written that here. Again, that's not so easy to show. That's fairly technical to show that you have to choose the background in one particular way, so that you get the right Gaussian factor. But that's not going to be relevant for us. I mean, you'll not miss out on anything. Basically, you just choose this alpha is to be square root of m. Okay, then Laughlin's wave function is simply given by the square root. So the only thing that I did extra is to insert this q, and this q will be chosen in such a way that the background Gaussian comes out. Okay, so there are some important things. So firstly, this alpha has to be some square root of m, where m has to be a positive integer. And the reason for this is a wave function which is fully written in terms of electrons. So any electronic wave function has to be single value. Okay, so if you had not chosen alpha to be like root m, where m belongs to positive integers, this wave function will not be single. So that's an important condition. Okay, and the other extra part is this: you have to choose q in some particular way, so that it reproduces the Gaussian.
What's the problem you have?
Yeah, so that's not some simple form. So one simple form you can choose is just you take the vertex operator at minus alpha n, so that it exactly cancels this charge that is coming from alpha n here. But otherwise, you have to do something really complicated, which I can tell you later. It's not so straightforward.
Can I answer? I think I will answer. This psi, if I'm in the chiral boson, in the compact boson language, it does not correspond to the point where the chiral boson is a Dirac form and it is not a Dirac form.
That's correct.
Because it has dimension 3 halves and not 1 half.
That's correct. Yeah, so all of these subtleties, I'm not gonna.
For the situation where nu was not 1/n.
Yeah.
So the claim is that we still have enough wave
No.
function, but not.
No, because of this single value problem. I need this to be single valued. The final electronic wave function has to be single valued. So I'm forced to choose alpha to be square root. Okay, now how to do the quasi-hole operator. So you kind of like repeat this recipe. You choose some v beta at some point omega or w, which is where I want to place the quasi-hole. Okay. And now you do the same thing. You just insert this along with the electronic operator and you compute this correlation function. And this turns out to be, you'll get Laughlin as it is from just the electronic part. And this combined with all the psi's will give you a factor which is like zi minus w to the power beta root n. Okay.
You have to change Q here because background.
Yeah, you have to change Q again. That's so at every point the Q will change to reproduce the Gaussian.
It's some Q prime.
It's some Q prime, that's right, yeah. Right. So now you get some zi minus w to the power beta root m. Now again, you demand single valuedness for the wave function. And if you do that, then this beta has to be like p over root m, where p again has to be a positive integer. Because if p was negative, you will get poles in the wave function. And then if you set p to be 1, that gives you the minimal charged quasi. So basically this alpha tells you what is the charge of the operator because of this U1 symmetry of moving phi to phi plus a. So from that, you can basically see that this charge is like 1 over m. Because if you now look at this wave function, this just gives you the simple form, which is like zi minus w. And if you insert 3 of these together, you will get 1 hole in total. So is this point clear? So you can construct the Laughlin ground state and you can construct the Laughlin quasi-hole as some CFT coordinates.
And the quasi-hole is the lightest excitation.
Yeah, this is the minimally charged quasi-hole. We call this minimally charged. So now you can have higher charged quasi-holes where you have like 2 of these together or 3 of these together. 3 of these together is like a single hole. So if I put 3 factors of this together, then that's exactly 1 hole.
What is the error because of putting a fractional?
That depends on the Hamiltonian, right? So that's a non-universal answer.
So what I was trying to ask is whether this quasi-hole in a CFT language is like a primary excitation.
Yes, it is, because this is the smallest value of P. So let me also say why this is called quasi-hole.
Yeah, that's what.
Yeah. So why this is called quasi-hole? Because the density of electrons there is 0. So if I now want to approach, if I want to put 1 electron at point W, then the wave function vanishes there. So that's why this is a quasi-hole. Okay, that's hole means deficiency of electrons. And it's quasi because now instead of like removing charge E, you're removing charge E over M. That's why it's called quasi-hole. So yeah, even if you didn't know any of this, you can actually show, there is a nice way to show that this has a charge E over M. Basically, you take this wave function and you do Monte Carlo with it and check how much charge is removed compared to the background charge, and that will give you E over M. Yeah, because I can do this for like very large system sizes.
You're going to do some G of R.
No, rho of R,
Oh, sorry.
just density.
Yeah, just
Density. So it will look like this. Chop, that's it. So if you look at rho of R of the Laughlin state, that will be flat because this is a uniform liquid. Now let's say I put W to be the origin, 0. Then the Laughlin quasi-hole will have a charge which is like this. It will have a density which will look like this. This is rho of R as a function of R. And you ask how much charge is in this thing. That will be exactly here.
And is it always in the loop some charge right?
You can also add charge. So the way to add charge is you change this to a derivative that will pull electrons together at that point. That's called the Laughlin quasi-particle. But the problem is when you have derivatives, that's not describable in terms of CFT. It's only these polynomials in Z that are easily describable in terms of CFT.
The derivatives like some sense.
Yes, that's the problem. So
Why is it they're not describable in terms of the CFT?
So there are some complications. So I mean, you can describe it in terms of descendants, but let's just say they're not described in terms of primary fields. Right. Yeah, let's.
But descendants are also perfectly fine objects.
They are fine, but you need to then do some more things. Like there is some screening condition and so on that needs to be.
Trying to say they suffer from stronger finite size effects.
No. There is no finite size. This is a wave function that doesn't care about any size. Yeah.
Right.
I am just writing an ansatz. But so whenever you write some wave function from CFT, it doesn't always necessarily have to give a good description of a state. So there can be some problems with the CFT. But I'm going to just shed some light on that in a couple of slides. So just because you write something doesn't mean it's legitimate. Let's put it up. Okay. So basically, to just summarize, what is the CFT approach to FQG? Is that you can now pick your favorite vertex operator and compute its correlators. Okay, and that will give you some candidate holomorphic wave function. Okay, that can potentially describe some ground state or some low-lying excitations of a quantum Hall system. So this is a major problem, that there is no general proof that this approach will generically work. So just because you manage to write down some holomorphic wave function, it doesn't necessarily have to be a description of a gap ground state. That is not given. But what at least I'm going to tell you about is there are some states for which there is no, sorry. Yeah.
I don't understand.
So just because you write some holomorphic wave function, that does not mean it can always describe some gapped ground state.
But if that wave function is same as the free state, then
We're not talking about Laughlin. Now you can do this for any vertex operator. So now
the question is, can you find the meaning of the vertex of
that's exactly, which can describe a gapped incompressible ground state.
So the crucial thing is gap.
Gap, yeah, that's the problem. Because otherwise it will describe some critical theory and so on. Exactly. So for example, in principle, you can also do this with irrational or non-unitary CFTs, but then we believe that those don't describe gapped states. They describe some compressible phases or some critical points between two gapped phases. So just because you write some holomorphic wave function doesn't mean it is
Because usually CFTs describe massless.
1 plus 1D gapless states, exactly. So
Yeah,
So-
but aren't you looking at the, approximation of the, lowest Landau level?
yes,
So that, and you're not, describing the whole system. So,
let's say the whole system is just lowest Landau level.
but it's not.
No, in numerics or in, let's say, I can always define my problem to be the Hamiltonian restricted to the lowest Landau. Let's forget about experiments for the time being.
So, the fact that, the system is, jacked or not wouldn't really.
No, that is a property of the interaction, right? For some so you can have the same state, but with a different interaction, it can become gapless.
Yes, that's true. Because it's a hugely degenerate
Yeah.
manifold, then there are some complicated quantum superpositions. It's not obvious whether the state will be gapped or gapped.
Yeah, and that is an interaction dependent thing because the matrix elements decide whether the next state is gapped.
Yeah,
or not.
classically it's all degenerate.
Yeah, so just because you can write some holomorphic wave function doesn't mean it has to describe some gap state. Okay. So here are some well-known examples of some CFTs that people have used. So these are the CFT-inspired wave functions that I'm going to be considering. So the Laughlin state you already saw, you just write the chiral Bose operator. So then there is this other famous state which is called the Moore-Reed-Pfaffian state. So there what you do is that along with the chiral Bose operator, you insert an Ising field. Okay, and that gives you this Pfaffian wave function at some filling factor 1 over m. Then there are generalizations of this. You can take like a ZK parafermion field, choose some some operator from that along with some Bose vortex operator, and that gives you some other state. So these are the three that we'll mainly consider. This is called the Laughlin, this is the Moore-Reed. And this, if you choose the Z3 state, is called the Reed-Rezai state. Okay, so now I'm going to tell you where these can be relevant. So before that, what do these wave functions look like? So there's one nice picture that Capelli et al. Came up on how to write down wave functions for these. So the construction goes as follows. So what you do is that you take n particles and you take k layers. Yes, there are these k layers. So here's an example of 3 layers. And you make a Laughlin state of bosons in each of these layers. Okay, so for the first part of the talk, we're only going to look at bosons because bosons are just simpler things to look at. So every time you have some layer, you construct a bosonic Laughlin state in it. And then what you do is you symmetrize the system across all of these layers. Okay, so this actually gives you exactly the state that Reed and Rezai had proposed when you take the ZK parafermion thing. Okay, so the way this wave function goes is I write down a Laughlin state, and then I take product over all of these layers. And then from outside, I have to like symmetrize this across all of the layers. Okay, so let me give you some examples. So when you have just one layer, then there's nothing to symmetrize across because there's only one layer. So there you just get the bosonic Laughlin state with m equal to 2.
Just one naive
Yeah.
question, so sorry. So, I mean, okay, so I should not think of this thing as a CFP, rather, as you said in the beginning, it's just a CFP inspired waveform.
That's all.
That's all.
Yeah.
It's not a CFP.
Mhm.
Yeah.
But you might be lucky and you can get some properties of this from the CFT, which might then apply to these things. Like you might be able to read off some quantities using the CFT. Like what is the edge theory and so on.
But for example, there's no notion of a central charge or these
No, there is a notion of central charge
or
because
OP coefficients. Or
OP coefficients, for the Ising CFT, we know what the OP coefficients are and so on.
No, but
But for this state,
Yeah,
yeah,
exactly.
but that central charge can be transferred to this state. That can happen. So let's say if you look at the Moore-Reed Pfaffian central charge, it happens to be 3/2.
Okay.
And that 3/2 you get because you have a chiral Bose operator and an Ising, which is a
What's that-
Majorana.
But what's the ramification of that 3/2 in the?
So now let's say you go to the quantum Hall system and measure its thermal Hall conductance.
Right.
That would be 3/2 times the fundamental constant of thermal
Oh, I
Hall.
see, because
Yeah.
that's related to the degrees of freedom.
Exactly. So you have half of a fermion, which is a Majorana, which is exactly coming from the Ising CFT you inserted, and a chiral Bose operator. Sorry.
But isn't the actual point that if you put boundaries on these?
Yes.
All things that are actually conform
Yeah, that's-
Atlas edge modes.
Exactly. So that is what carries the thermal Hall. The thermal Hall is carried by the gapless edge mode, which happens when you put this system next to a vacuum.
Okay, now it's a bit clear. So you're saying if I just look at the boundary theory,
Yes.
then that's a gap distance.
That's a gapless that can be described by a CFT, by the same CFT. Sorry.
And the wave function, how to get a boundary theorem?
No, from the wave function you can't, but from how I came up with this wave function, you use these edge operators, from that you can. Okay. So this construction is clear. You take k layers, construct Laughlin in each, and then symmetrize. Okay. So let me give you some examples. So when there is only one layer, there's nothing to symmetrize. There's only one layer, so then you just get the bosonic Laughlin state. Then for k equal to 2, you actually get a state which is called the Pfaffian. So this symmetrized phi1 square actually. So this phi1 is this wave function of 1 fill Landau level. So this I will sometimes call as phi1 square because it's just 1 fill Landau level repeated. This, owing to some identity due to Cauchy, you can show has exactly this form, which is like Pfaffian of 1 over Zi minus Zj times this Zi minus Zj. Okay, so this is a non-trivial statement. It's not easy to see that this symmetrized phi1 square is exactly this. But it turns out that it is. And this Pfaffian you kind of get from this Ising part. And this Zi minus Zj you're just getting from the chiral Bose. Okay, and for k equal to 3, you get a state at nu equal to 3/2 and so on. Okay, and fermionic states can just be constructed analogously because I have a symmetrized state. Now all I do is I multiply it from outside by this factor, which is nu equal to 1, and that will anti-symmetrize the whole thing. So it's sufficient to just look at bosonic states because fermionic states they come for free. But it's actually the fermionic states that are relevant for experiments. So if you look at k equal to 1, you get 1/3 Laughlin. K equal to 2, you get the 1/2 Moore-Reed. K equal to 3 is this nu equal to 3/5, which is called this Fibonacci state of Reed and results. Okay, so what is some experimental evidence for these? So it turns out that if you look at fractional Hall states in the second Landau level, so by second Landau level, what I mean is you fill the lowest Landau level of up and down spins completely. And in the second Landau level, you have a fractional fill. So I look at the n equal to 1 orbital with upspin, and I have a fractional filling in that, then actually some of these states can show up. So for example, there is a state at 2 plus a half, which is this famous state at 5 half, which is believed to be described by Moore and Reed's wave function. Okay, then there is this state at 2 plus 2 fifth. This is believed to be described by the Reed-Rezai Fibonacci state. So some of these RRK states can underpin fractional quantum Hall states in the second order. Okay.
So these numbers that four feet.
Yeah.
Is there any explanation for why these specific numbers?
Yeah. So you can write a sequence which will produce these in some order.
And are these CFTs understandable by just sort of using some minimal
Exactly.
models and stuff like that?
I mean, what do you mean by minimal models? Like, if let's say I take Ising and Bose and fuse them together, you can come up with the CFT first.
So you're saying the C to 3 by 2 is 1 plus half.
Exactly.
Yeah, so that's just simple fusion.
That's all. So in general, for the ZK parafermion, it will be 1 plus the central charge of the parafermion. Because the chiral Bose always has 1. Sorry.
From the point of view of CFT, what is the fact? Two CFTs interacting?
You have some interaction between the two CFTs. But effectively, because of this OP separation, you can just separate them out and then look at these two things.
Actually, effectively, they're not interacting.
Effectively, they are not interacting. Yeah, that's what I was going to say.
Because
So,
if it were interacting,
no, then the number will
it's
change.
not-
Yeah, then the number will change.
In the second Landau level, you don't even have holomorphic, shouldn't have holomorphic functions.
No, so that's the beauty that Duncan showed. So what you can do is this, whether you're in second Landau level or third Landau level, that whole thing doesn't matter. You can always look at the state in the lowest Landau level, but just change the matrix elements. Okay, so you now change the matrix element so that second Landau level is simulated in the lowest Landau level. So you can continue to work with holomorphic wave functions. That's the whole idea. As long as you project to a particular Landau level, the only thing that tells you the Landau level information is the matrix element. Now I will use the Coulomb matrix elements for the second Landau level, but use my basis as the lowest Landau level, and then you can then still continue to use these wave functions. So effectively, the way to think about this is this n equal to 0 up and down, they are totally inert. They are completely filled. They play no role in the game. Then you have one Landau level which is half filled. Whether it's lowest or second doesn't matter. I will just tweak the Coulomb matrix element to simulate whichever one I want. This is an experimental trace. So this is the longitudinal trace, and this is like the Hall trace. So every time you see like a dip in RxX roughly, this dip or this dip, they correspond to some plateaus because that's a sign of a gap. So this 2 plus a half is a big dip here, and 2 plus 2 fifth has some dip here. So every time you see a dip in this, and concomitantly you should see some plateau in the Hall resistance. So let's say you're at 2 plus half, you see some plateau.
I don't know if possible or gas, but how do you know this is the second one?
Because I tune the electron density so that the filling is 2 plus something.
Explain.
Yeah, in experiment, I just tune the electron density so that I fill. I have control over both the magnetic field and the density of electrons. Okay. So the Moore-Reed state, as I've shown, has this particular form. So there is a way to interpret the Moore-Reed state as a patch state of some objects which are. No, sorry.
Sorry.
No.
So if you go to these higher fractional quantum Hall states then, and experimentally look at these edge modes,
Mhm.
then there should be a separation of these edge modes into more basic objects, right? Because they're just fusing things. So is it hard to see?
That's very hard to see. That's because it should happen. Like for example, the lowest Landau level mode should be separate from the second Landau level mode. Simply because if you look at the confining men,
Right.
the lowest Landau level goes separately, then the second Landau level goes separately. But it's experimentally they're really close.
Yeah,
and-
because they're in the same
That's the
spaceship.
problem, yeah. But for example, if you measure thermal Hall and you get some half quantized answer,
Correct.
that would be a sign for Ising. That is what people are trying. Okay. Yeah, by the way, I forgot to say this. So for the Moore-Reed and this 3 cluster Reed-Rezai state, they happen to be non-abelian. So there is some interest in these states simply because their excitations are non-abelian anyons, and you can make like a fault tolerant qubit out of this, but that's far away in the future.
Yeah, I mean, I have something very important. So this split that you are saying is it's sort of, I mean, if you think about something like that, kind of resonate model,
Yeah.
say on, I mean, SU2,
Mhm.
So you can split it up as an animation to mod U1 cross the U1.
Yes,
Which is what exactly.
Exactly,
you
this is that, yeah.
You are doing, right?
yes,
But that's a your parafermions are SU to mod U1s.
Yes.
And then the U1 is your.
Chiral boson,
The extra.
Yeah.
Chiral boson.
perfect.
But that's a split that you made in your system.
Yes, I did.
How, why is this, why, applied.
Why should that be realized?
Yes.
Yeah, so there is no guarantee for that.
Yeah.
So what this split allowed you to do was to write a candidate wave function. That's a different question on whether this candidate wave function will be realized in some setting.
Right.
That is an interaction dependent statement. For some particular interaction, you can actually show that the candidate wave function will be realized. So let me do that.
I mean, you can analytically.
You can analytically show. So here is the trick. So let's say I look at the wave function of this kind. Then this is actually an exact ground state of a Hamiltonian where you bring k particles together. It's an exact zero energy state of that Hamiltonian. Let's go back to this layer picture. So for example, when I bring two particles together in the Laughlin state, so if you have a state of bosons, then in general, if you write down an expansion in terms of the relative coordinate between two bosons, the expansion will go as r to the 0 plus some r square plus r to the 4 and so on, right? Because these are bosons, only even powers will show up. So now what the Laughlin state does is it gets rid of r to the 0. Because every time I have a factor which is like this, then if you let's say have a delta function interaction, then the Laughlin state has 0 energy for that. Okay, so now I have a delta function interaction for let's say 3 particles. I put a delta function when 3 particles come to one point. Then the Moore-Reed state will be an exact zero energy state of that. Because you can bring 2 particles together in opposite layers, they don't talk, but when you have to bring 3 particles, you have to necessarily bring 2 from the same layer together. So then all of these Reed-Rezai states are exact ground state of k plus 1 body Hamiltonians. So for that system, this is exactly going to be realized. But that model Hamiltonian has got nothing to do with the Coulomb interaction. So whether it's realized for Coulomb is a different question altogether. But there exists some model Hamiltonian for which these will be realized. That I can demonstrate this way. Okay. So this Pfaffian state actually happens to be like a P-wave BCS superconductor of some exotic objects which are called composite fermions. But again, you can forget about all of this and just look at what is the overlap of this with the exact second Landau-Levy Coulomb ones. I mean, that's a question one can ask. And that overlap for a fairly large system is like about 70%. So it's not as impressive as Laughlin, but it's pretty good. And you can do the same for this 3-cluster Reed-Rezai state.
But sorry, coming back to this previous question.
Yeah.
The belief is that if you just change the interactions a bit, so that of course.
Yeah, as long as you don't close the gap, you'll be fine. Yeah.
So there must be a more universal way of thinking about.
Yeah. So the question is that the question is whether there is an adiabatic path that takes you from this model Hamiltonian to the experimental interaction.
So the key word you said is no gap.
No gap closing. Yeah.
So
Adiabatic path means there is no gap in between. You do that slowly, and there should be no gap closing in between. So if there is no gap closing, you cannot transition to some other state. But that's very hard to establish. That's the whole point.
Yeah.
Okay. So this 3-cluster Reed-Rezai state, you kind of write like this. So I make 3 clusters. In one cluster, I call the particles U. In another one, I call them V. In another one, I call them W. I make a Laughlin state of bosons in each of them. And outside, I multiply overall by a factor of 5, so this becomes a fermionic state. And again, its overlap with this exact Coulomb ground state is about like 81%, which is again super high overlap. Okay. So now the question is, how do we work with these wave functions? So you can see what the problem is. The problem is doing this symmetrization is extremely hard because symmetrization grows factorially. So when I say symmetrization, what do I actually mean? I mean that you sum over all permutations. Okay, so you look at Sn, which is the symmetric group of n particles, and you construct this state for every permutation and sum all of those up. Okay, so that's not going to be possible when n is like roughly like 20 or something. So actually here you can do something better. You don't have to actually sum over all permutations. You can sum over some reduced set of permutations. So the reason for that is as follows. So every state, every Laughlin state is actually symmetric. because you don't have to exchange any particles within each layer because they are already symmetrized. Okay, and each of these clusters themselves form the same state, so they don't have to be symmetrized either. So that brings down the number of permutations down by like k factorial times n over k factorial to the power k. But still, even this number is pretty large. This still grows factorially. So how do we actually, as I said, we want to do Monte Carlo, and how do we do that when the number of terms to handle is so many? So hopefully the problem is clear. So, okay, so the trick is the following. So what you do is that in anytime you have a wave function, the thing is that you're not really interested in the wave function, but you're mostly interested in some correlators of it or some energy computation for it. So what I'm going to argue is that energies and correlators can be computed much faster than computing the wave function.
Are you trying to then say that you do some importance sampling?
No. No. The importance sampling I'm not going to do. I mean, I'm going to do importance sampling, but with something which will still reduce the. I mean, you have to do importance sampling to do Monte Carlo, but you have to do some reduction before you can do importance. Because if you just importance sampled with these many terms, you are basically cooked. So nothing else. Okay. So let's just, for the sake of illustration, just look at the Moore-Reed state, which, as I said, I'm going to call as symmetrized phi1 square phi1 square. If phi1, remember, is the nu equal to 1 integer Hall state, that you should remember is very easy to simulate with Monte Carlo. I showed like Laughlin state you can simulate easily with Monte Carlo. So this state is also very easy to simulate with Monte Carlo. So this state where you have this bilayer sort of construction, that's called a Halperin state. Okay, so that this is just some notation to say what the Halperin state is. This is called 2 to 0 because this exponent is 2. That's all. And the important thing is there is no interaction between these two tips. So each of them forms an independent Laughlin state. Okay. And the Moore-Reed state is just symmetrized over Halperin 2 to 0. So now what I'm going to claim is that if you want to compute a matrix element which is like this, psi1 O, psi1 MR, where O is a permutation invariant object. So let's say O was Coulomb interaction. Then O has this particular form which is sum over I less than j, 1 over zi minus ej. This operator is permutation invariant. It does not care about what particle indices are. So any permutation over the particle indices keeps this operator invariant. Matrix elements of these operators I'm going to claim can be calculated easily. So let's see how. Okay, so what I do is I first write down the Moore-Reed state as this sum over permutations of the Halperin state, and just write what this matrix element is. So it has this form which is like there is a P1 for this permutation on the left hand side, and there is a P1 on this, and there is an O operator which I'm assuming is permutation invariant. So now what you can do is you can slide this P1 through O, because O is permutation invariant, and P1 times P2 is another permutation. So effectively this thing gets reduced into just computing something like this. So you take the Halperin state with a fixed ordering of the particles, and you want to compute O times P on the other Halperin state. Okay, this argument is clear again. Okay, so it turns out that this matrix element takes very few distinct values. So that is the key idea, that even though this looks like this is a sum over permutations, the value that the matrix element is going to take is going to be, there are very few distinct values that these matrix elements can take. Okay, why? So I'm going to argue that this has only like n over 4 plus 1 distinct matrix elements. Okay? And the thing to appreciate is this is like a linear number in n. So we reduce the problem from something which was like factorial in n to something that's linear in n. And this you will be able to do with Monte Carlo. That's basically the argument. Okay, so why is it that this can take only so many distinct values? So firstly, phi1 square is already fully symmetric in its argument. So anytime you exchange any two particles here or here, within that single phi1 square sector, nothing will change. The wave function remains exactly the same. And the two clusters can also themselves be swapped around because they both form the same Laughlin state. So this matrix element gives the same result for any permutation, unless you swap exactly m of the indices from 1 to n by 2 into the set n by 2 plus 1 to n. Okay. So this is the crux of the argument. So there are only m equal to 0, 1, 2 up to n by 4 values, which will give me distinct matrix element. Every other matrix element is the same.
Sorry, I didn't even ask this.
This one?
Yeah.
Yeah, so I'm saying that, let's say I write this down and ask how many distinct values this can take.
Yeah.
So this can take only these many distinct values. So every time this exchange, so let's say I had one set from 1 to n by 2 and the other set from n by 2 plus 1 to n.
So you're saying that any sort of overlap will not.
Will not do because they form the exact.
That happens.
Yeah, so the only time that will happen is if you exchange some particles from here to there. And the only number of distinct exchanges you have is exactly n by 4. Because you can firstly exchange only n by 4 elements. Because if you exchange more than n by 4 elements, I will just swap the two clusters. So that's all. Okay, now the trick is very simple. Now, once this is established, you just compute n of these. And then you have to add them with the appropriate combinatorial weight. Okay, so you have to say how many m equal to 0 exchanges are there, how many m equal to 1 exchanges are there. That weight multiplied by the value of the matrix element for that exchange is the answer. That's it.
Is this like saying that matrix element only depends on the conjugacy class of the permutation, or it's more subtle than that?
It's, conjugacy classes of permutation, I know what exactly you mean by it. There is an equivalence class which is just set by one number, which is the number of exchanges. So maybe I'll give an example in case this part is not. There's no eraser. Okay, maybe I'll write it. So let's say you just take the simplest case, which is number of particles equal to 4. Okay. So then what I do is that I have these sort of permutations that I need to sum over. Okay, so as I said, it doesn't matter which thing you call the first cluster and which thing you call the second cluster. So now I have, let's say, the only permutations that matter here are these. So that's because of this argument that I gave. So if you look at this number, so let's say you have n factorial by n by 2 factorial square of this times 2 factorial. That number is exactly 3 for n equal to 4, because this is 4 choose 2 by 2. That's exactly 6 by 2, which is 3. So these are the 3 permutations. So what I'm claiming is that these two matrix elements are the same. Okay, so that's because you can exchange. So what has happened here is there is exactly one exchange that has happened. So let's say I take this as my base set. This is just a different name for identity permutation. Now you ask, how many exchanges have I done compared to the identity permutation? There is exactly one exchange here. There is exactly one exchange here. I took 2 and 3 and swap. I took 2 and 4 and swap. So wherever you have exactly one exchange, those two matrix elements will be the same. That's because these are just like dummy variables in this matrix element. You can just swap those around. That's all. How am I doing on time? About if I should finish. 15 minutes. 15 minutes. 15 including questions, right? Yeah. Yeah. So I'll probably finish. Okay, basically that's the gist of the argument, that the wave function is very hard to compute, but matrix elements are much simpler to compute, provided you look at matrix elements of operators that are invariant under permutation, which most of the operators of your interest are, like pair correlation, energies, pairwise energies, and so on. Okay. So how do we actually first compute what these combinatorial weights are? I mean, this is a simple exercise in combinatorics. So there's this combinatorial identity that you can use, which is like n factorial is the product of n by 2 factorial square times sum over exchanges, where n by 2 choose m to the power 2. So how do I get an identity like this? So the left hand side of this equation counts all possible permutations. And now what I'm going to do is, in the right hand side, I'm going to explicitly count these permutations by exchanges. So I have 2 clusters and I exchange m particles between these 2 clusters. So firstly, within each of these clusters, I have n by 2 factorial ways of doing things. So that's how you get this n by 2 factorial square. And then in each cluster, I have n by 2 choose m ways of picking m elements. And I have n by 2 choose m ways of swapping that in the next cluster. That's all. So that tells you what the weight for the mth exchange should be. Okay. Okay, so interestingly, just this naive approach actually does not work well in Monte Carlo. So So originally when we did this, we were very happy, like, okay, we found some way to do this, but it doesn't work out practically. And there's a good reason for this. So first, let me show where it kind of fails. So this full symmetrization means you just sum over all possible permutations. That's the brute force way of computing the wave function and just computing matrix. So this naive way is what I had just described to you. So you just compute each of these mth exchanges. You compute exchange for one representative term and multiply that by the combinatorial weight. Okay. So the issue is that when you take one representative term, then Monte Carlo can have issues in convergence. So what can happen is that this representative term may not average to its ensemble average in the time that you run the Monte Carlo. So although everything I said is analytically correct, practically speaking, when you do Monte Carlo, you can take a very long time to converge to the ensemble average when you're using only one representative out of these n. So for example, in this, for m equal to 1 exchange, I have two representatives, right? I have this or this. But what I'm going to do is pick one of these and run Monte Carlo only for that. Okay, so that might take much longer than if you had taken both of these and done average of those two Monte Carlo. So in the refined method, what we do is that we average over many representatives. That's all. So that gives us much better and much faster convergence. So that's what we call the refined method. Basically, the idea of the naive method is what you should take home. So that's the main idea. But practically, you just need to do more representative to make sure that the Monte Carlo converges. So this in the Monte Carlo parlance is called the mixing time. So this mixing time you can bring down by adding more representatives for a given exchange class.
But in principle, if you do it,
Then just the naive will work. So for example, if you do a smaller system, then you can run that for a very large number of iterations, and there we show that it matches.
The reason why this full one is completely off is just because you can't sample all the permutations.
Exactly,
And also
that's-
you can get a
yeah.
variable representation.
Perfect. Exactly. Okay, so this refined method then is what we use, and that we kind of show works well for all of these, like Moore-Reed state, the Reed-Rezai state, and so on. So for small systems, you can just check against exact diagonalization, or for the Moore-Reed Pfaffian case, you have this advantage that the Pfaffian square is actually the determinant. So you can just do Monte Carlo with the determinant, which is again very fast because determinant of Monte Carlo is only like order n cube. So these are results computed from that exact construction of the state in Fock space or this Monte Carlo of the Pfaffian. And our results match with them for like 3 decimal places. So energy is one thing, but we can also like capture correlation functions fairly well. So in this plot, we are showing the correlation functions computed 3 ways. So there is this full symmetrization, which is of course bad because you're not able to like sample. And then there is this naive and refined compared with this green line, which is the exact. And essentially the blue dots track this green line really well. So once you do this refined method, you can get pair correlations and so on very well. So this is basically my final slide. So for Moore-Reed, anyways, we don't need this method because for Moore-Reed, there is this Pfaffian which squares to determinant. And as I said, most of the times you're interested in mod psi square. So mod psi square for a Pfaffian is just determinant. That makes it very easy to compute for Moore-Reed. But that's not the case for this 3-cluster Reed-Rezai state. So there you really need this method to like show, to be able to compute things for large sizes. Again, we can kind of show that for all of these systems, for the largest size for which we can construct the Reed-Rezai state from exact numerics or Fock space computations, there our correlations match with them very well. Okay. Okay, so the main, so let me summarize what I had to say. So energies and correlation functions for wave functions that require explicit anti-symmetrization or symmetrization can many a times be easier to compute than just the wave function itself. So let's say you have a complicated wave function. It may be the case that you cannot compute things you cannot like compute the wave function easily, but you can compute some matrix element for it easily. And eventually at the end of the day, you only care for these matrix elements. So let's say if I want to study how well does this state compete with some other candidate state for pi half or for 12/5, then the only thing I need is some energy computation. So that you can compute efficiently for permutation invariant objects, even though the wave function is very hard to compute. So the next thing we want to do is to actually show that if you let's say take the Reed-Rezai state, it does have Fibonacci anions. So the thing that you need to like demonstrate these anionic statistics is like you have to keep the particles far away from each other, because otherwise what happens is if they overlap with each other and then the anion computation is actually messed up. And to keep these anyons far away from each other, you need to get to very large sizes. And that you can never do with Fox space type of computations, but that you can do with Monte Carlo computations. So that's what we want to do next.
So to show that these are anions, you have to somehow break them.
Yeah,
How will you do that in a Monte Carlo?
you move the state and you compute some matrix element again.
I see.
And then you look at what is the unitary matrix that you get at the end of the whole breeding. And if that matches with your expected thing, you claim that this is Fibonacci.
It's not very easy.
It's not very easy, of course, but it's doable in Monte Carlo. So for example, for Murid, this is already
You
been.
have to do some unitary operation so that one guy is fixed and the other guy moves in a closed path, and
Yes.
you have to measure the phase.
That's all.
But these are non-abelian anions.
More than phase, you have to measure the
Oh, yeah,
state.
that's correct. You
Yeah.
have to measure the state.
Yeah.
Yeah.
For abelian anions, basically what you said is what you
Yeah.
did.
But also like these non-abelian anions, not just this state, they also have this interesting fusion, right? That
Yeah.
this you can this
Fusion we can't measure very easily.
cannot see.
Yeah. But the idea is that if one of these things works out well, basically it should all be there. All be okay. Wow. Okay, so let me end with some acknowledgements. So Koina did most of all the heavy lifting. And some of these ideas were originally due to Steve. So Steve kind of came up with the naive method, but he was stuck because he didn't think of this refinement. And then that was our main contribution. Okay, I'm stopping and I'll be happy to take any more questions.
Questions?
Yes, one question is sort of related to what I asked previously. So of course, when you do these E/3 experiments, like transport experiments, people literally put an electron and then they see that it fractionalizes into E/3. Yeah, when you do these short noise.
Short noise is like that, yeah.
Right. So, I mean, okay. So in the first part of your talk, you of course talked about this ground state and having these specific vertex operators which give you
Yeah.
E/3. But is there any analog of doing this thought experiment in terms of operators that I actually insert an E and then I see it fractionalize?
So there is a way to do this using STM. So let's forget about the edge. Let's look at the bulk. So what I do is in the bulk, I insert an electron.
Yeah.
And then I ask what are the bound states that these electrons can make out of E/3 particles.
Right.
So now if you do tunneling spectroscopy, you should be able to see these bulk states.
No, but there must be a way to see this even in this operator language and wave functions, right? So-
Yeah. So the wave function language, you just take like, let's say you had this as the single quasi-hole
Right.
on Laughlin. Then the way to insert an electron is to insert 3 powers of work. 3 volts of work.
Yeah, but then how do I see that they can fractionalize in E/3?
Yeah. Then you just separate them out. So here I inserted all of them at one
Oh, I
point.
see. Yeah, okay.
Now with the tunneling thing, you
Yeah.
can probe and move them around.
And that's like the lower energy guy then.
Yes, that is much lower in energy than this. Now when you bring them close together, they can form tightly bound states which can ramp
But
up
that
the
gives fit in.
Yes,
Yeah.
but in tunneling spectroscopy, you can actually have energy as a knob because voltage is a knob for them.
Correct.
In tunneling spectroscopy, how do you measure this fractionalization happen? Because you can only transfer electrons.
Yes,
Because it's
but-
out of the.
But every electron will then fractionalize into these. Only way the electron can go. So let's say you're at very low voltage. Then the only way that the electron can go into the system is if it fractionalizes into 3E/3 particles. So there is a very specific bound state of this 3/3 particles. Otherwise, you will not be able. You'll see tunneling gap. Otherwise, the electron will not be able to go through. That's all. So effectively, let's say you had some orbitals and you inserted electron at a particular point, that would be like emptying these 3 holes. Exactly. That you will see. That you can see because you know what is the energy of putting exactly 3 quasi-holes in these 3 orbitals. That will match the electron insertion energy.
Do the energy observables and the correlation functions that we will configure later on?
Yeah.
Will also correspond to some object in the chiral boson theory?
Yeah, so this is not chiral boson. That's the this is not. So this was not for chiral boson. This is for this Ising. So here you take the Ising CFT times the chiral boson and compute correlation function for that. This is exactly that combination.
But I guess what you're asking is if these matrix elements have
Yeah,
some
itself is
information
something
in
exact.
safety.
So-
Exactly.
If these matrix elements have what? Some connection to.
Yeah, is it itself a CFT object? Some
Oh, just the
CFT
full-
equation.
I don't think so, because the way this is like a non-local correlation, you let's say insert the Ising CFT and the vertex operator at some point,
Mhm.
and you do this at some, maybe that's possible to measure in, maybe that's possible to
I
compute.
think these things are related to some universal data and CFTs, right?
It's possible.
There's some correlation function which is somehow you have to form some asymptotic thing and maybe.
So
because-
my recollection is that if you let's say you Fourier transform this and you get like a structure factor out of this correlation function, then the long wavelength expansion of that is fully fixed by CFT. But not otherwise. Not the full thing is not fixed by CFT. So if you let's say look at the S of Q data, and again because this is a uniform state, this has some expansion which is like Q square plus Q to the 4 plus Q to the 6 and so on. So these three coefficients you can fix with CFT, but not beyond that.
But that's basically related to the fact that when you have some physical realization like that and you measure some local operator.
Yeah.
And you try to express it in terms of CFT primaries and descendants, you get everything. You get primaries and descendants. So then when you look at things asymptotically,
Yeah.
the contribution from the primary.
Dominates. That's fine. Yeah, I think this part is okay.
Yeah.
But can you get the full G of R? I don't think that's possible. Like, can you get the full S of Q? Even actually, it's an open problem to determine what is the Q to the 8 coefficient for this.
So it's also 4. So if there are no other questions, let's end the session formally.
Thanks.
Thank you very much.